You are listening to The Vocal Technologist. Spoken tech for your ears.
You sit there watching a pipeline stall for 30 minutes or an environment take an hour to clone, and you honestly start thinking, is it me? Like, is the universe actually out to get my deployment?
Oh, yeah, it really does feel personal sometimes.
It completely does. You start questioning your life choices, your configuration files, maybe even the alignment of the stars. It is basically the spinning wheel of death, but, for infrastructure.
Right, and it just drains all the momentum out of your day.
Exactly. I am your host, just a tech-savvy mate who has stared blankly at a terminal window while the coffee gets cold, and we are going to look under the hood of the modern infrastructure stack.
And I am here to bring a bit of the analytical side to things to help pull apart exactly why these systems behave the way they do.
Spot on. Because we have pulled together this massive stack of engineering postmortems, pull requests, and threat reports to explore what happens when the universe really is out to get your deployment.
Yeah, we are talking about everything from literal hardware bugs breaking fundamental logic to massive repository bloat.
And even how the entire ecosystem is essentially being rebuilt to just, hand the keys over to artificial intelligence. So let us get straight into it.
I want to start with that feeling of dread you mentioned. When those deployments hang, we build these incredibly complex systems, right?
Yeah, heaps of moving parts.
Exactly. And when they grind to a halt, our initial assumption is usually that we have made some massive architectural error. We sort of assume the failure must be proportional to the delay.
Right, like if a build takes an hour, we assume we need to rebuild the entire continuous integration pipeline from scratch.
Spot on. But when we look at the mechanics of these failures across the industry, we start to see a much broader picture. It is not just about making things faster anymore. It is about fundamentally changing who or what is actually driving the system.
Okay, but let us unpack that assumption about proportional failure first, because sometimes the biggest bottlenecks are hiding in, like, a single line of configuration, or maybe some legacy heuristic that no one even remembers is running.
Oh, absolutely. Take the situation with Cloudflare and their Atlantis deployments.
Ah, yes, Atlantis.
Yeah.
For context for you listening, Atlantis is this highly popular automation tool for infrastructure as code. It basically listens for pull requests and runs the deployment commands automatically.
Right, and Cloudflare was experiencing these 30-minute restart times for this tool.
Which is just brutal. That is 30 minutes where engineers are completely blocked from pushing changes.
It is an absolute eternity in a modern engineering environment, especially if you are, trying to push out a critical hotfix.
So what was the actual problem? I assume people were looking for some massive database query locking up.
Yeah, or like a severe routing loop. But the culprit was literally a single Kubernetes setting.
Okay, one setting.
Just one.
Wow.
The default policy for changing file system groups, which is known as S-group change policy, it was set to always.
Okay, so what does that actually mean in practice?
It meant that during every single restart, Kubernetes was recursively changing the ownership permissions on millions of files within the persistent volume attached to Atlantis.
Oh, wow. Let me put that in a real-world perspective for you.
Yeah.
It is like having a security guard at a massive office building.
Yeah, that is a good way to look at it.
And the policy is set so that every single time one new person walks through the front door, the guard forces every single person already inside the building, like thousands of people, to come all the way down to the lobby and show their identification again.
Yes.
Every single time the doors open.
That captures the sheer scale of the computational waste perfectly. It is just redundant work destroying operational efficiency.
So how did they fix it?
The fix was almost embarrassingly simple. By changing that single policy setting from always to en route mismatch.
Okay, so en route mismatch.
Yeah.
Meaning it only checks if something is actually wrong.
Exactly. The system was instructed to only check and change permissions if the root owner actually differed from the expected volume permission.
So the security guard stops checking everyone in the building and only checks the new arrivals.
Spot on. That one-line fix eliminated the bottleneck entirely. It saved them roughly 600 hours of blocked engineering time per year.
600 hours from one word in a configuration file. That is equal parts amazing and straight up infuriating.
It really is. And you see the exact same phenomenon with Dropbox. They had a similar revelation, but it was with repository bloat.
Well, monorepos. For anyone who has not suffered through one, a monorepo is basically bumping every single piece of code your entire company writes into one massive repository.
Yeah, they can get huge. And Dropbox slashed their server monorepo from 87 gigabytes all the way down to 20 gigabytes.
That is a massive reduction.
It is. And they cut their clone times from over an hour to under 15 minutes.
So they must have just deleted heaps of old code, right?
See, that is the wild part. It was not even excess code slowing them down. The bloat was caused by a quirky interaction between their directory structure and a Git compression heuristic.
Okay, you're going to have to pull apart how a compression heuristic causes an 87 gigabyte bloat.
So Git tries to be incredibly clever about how it stores data. Instead of saving full copies of every file every time a developer makes a change, it uses a compression heuristic to find similar files.
Right, and it only stores the differences, which we call deltas.
Exactly. But to do this efficiently without scanning an entire 87 gigabyte repository every time, it uses a shortcut. It only looks at the last 16 characters of the file path to find potential matches.
Okay, so it sees two files ending in the exact same 16 characters, and it just assumes they are related versions of the same file. I can see how that speeds things up in theory.
In theory, yes.
Where does that go catastrophically wrong for Dropbox?
Well, Dropbox has a massive amount of internationalization files. Think of files named for specific languages nested deep in specific feature directories.
Right, okay.
The paths leading up to those files were very similar, and the last 16 characters were often identical file names across entirely different language dictionaries.
Oh no, so Git was getting confused.
Very confused. It was trying to create delta comparisons between an English translation file and a Japanese translation file.
Oh, wow. So Git is sitting there churning its gears, trying to calculate the mathematical difference between two completely distinct human languages.
Yeah, generating incredibly inefficient and bloated compression files in the process.
It is literally trying to find the delta between the English word apple and the Japanese kanji for apple.
And doing that across thousands of files, it was just a mismatch between a foundational tool making a well-intentioned assumption to save time and the specific architecture of the Dropbox codebase.
That is wild.
By working with GitHub to optimize how that heuristic handled those specific paths, they achieved that 77% reduction in repository size. It just highlights how much invisible heavy lifting our tools are doing behind the scenes.
Yeah, it is almost a relief when we can blame our own configurations or, a quirky software heuristic. But here is where it gets properly weird. Because what happens when the literal silicon foundation you build upon betrays you?
Yes.
Like, we are so used to scrutinizing our code, but we never really question the metal itself.
We are definitely trained to trust the hardware unconditionally. We sort of assume the physical chip is an immutable truth.
Right.
But the team working on RocksDB, which is a massive high-performance storage engine used across the industry, they ran a stress test and discovered something fundamentally broken at the silicon level.
Yeah, they uncovered a hardware bug where certain central processing units were incorrectly returning predictable values. And this was from a very specific instruction called RD-seed.
Exact.
And just to be clear on why that is terrifying for you listening at home, the RDE-seed instruction is designed to generate random numbers. It reads from an on-chip entropy source, which is basically physical electronic noise, to provide true random numbers.
Which is critical.
You need those numbers for literally everything, from generating unique identifiers in databases to encrypting your passwords.
And because of this hardware defect, it was returning predictable, repeating values. It broke fundamental assumptions about randomness across the entire software stack.
So what did that actually do to RocksDB?
Well, it caused the system to generate duplicate identifiers, which ultimately corrupts the database. When a literal computer processor forgets how to generate a random number, you realize you can have the most perfectly architected software in the world.
And it will still come crashing down if the physical chip is lying to you.
Exactly.
Which, yeah, it's exactly as terrifying as it sounds. But it also works in reverse, right?
How do you mean?
Well, if a hardware bug can break your software, a massive hardware upgrade can also force you to perform incredibly painful software rewrites. Look at what Cloudflare went through with their Generation 13 servers.
Oh, the AMD processors.
Yeah, they rolled out these massive new servers powered by advanced AMD processors. We are talking 192 cores per processor. Just an absolute beast of a machine.
But there was a significant catch. To physically pack 192 computational cores onto a single silicon chip, the hardware designers had to trade away something else.
Right. They sacrificed the size of the level 3 cache memory.
Yes.
And the level 3 cache is the rapid access memory that sits right next to those cores. It is the extremely fast scratch pad the processor uses, so it does not have to go all the way out to the slower main system memory just to fetch data.
Exactly. So they get all these shiny new computational cores, but they lose the rapid access scratch pad.
So how did their software handle that?
Not well. The problem was the legacy request handling stack at Cloudflare. Their system, known as FL1, was heavily reliant on NGINX.
Okay.
And the way NGINX processes worker requests depended entirely on having a massive level 3 cache to function efficiently.
Oh, I see where this is going.
Yeah, when Cloudflare deployed their existing software onto this brand new, incredibly powerful hardware, the reduced cache caused massive, unacceptable latency spikes.
Because the software was constantly waiting for data to be fetched from the slower main memory.
Precisely. The new hardware actually made their system significantly slower because the software was shaped for older silicon architecture.
So they cannot just return the servers, right? They have to rewrite the software to fit the new physical shape of the hardware.
They had no choice. They had to completely rewrite that core request layer from scratch.
Wow.
They built a new system called FL2 using the Rust programming language. Rust allowed them to build a highly concurrent system that did not rely on large cache pools to handle thousands of simultaneous connections.
I mean, rewriting your core layer is a massive undertaking.
It was, but it ultimately allowed them to achieve double the performance and 50% better power efficiency.
But it is not just the hardware layer feeling the strain of modern scale, is it? That exact same performance ceiling is forcing the compilers and networking tools sitting on top of the hardware to completely rewrite their own DNA.
Oh, absolutely. You can see this panic happening right now in the JavaScript ecosystem with TypeScript 6.0.
Yeah, explain what is going on there.
Well, TypeScript 6.0 is entirely a transition release. It is introducing new alignments and deprecating legacy options for one specific reason.
They're preparing for version 7.0.
Yes, which is going to be a massive foundational overhaul. The current JavaScript-based tooling has just hit a performance ceiling. It simply cannot compile massive code bases fast enough anymore.
So what is the fix?
Version 7.0 will be rewritten in the Go programming language to achieve high-performance compilation.
And we're seeing the exact same structural evolution in the Kubernetes ecosystem too. Like, version 1.36 is forcing a major networking evolution.
The ingress controllers.
Right. They're retiring the legacy ingress NGINX controllers. For those who might not be deep in the weeds of cluster routing, ingress controllers are basically the traffic cops that route external internet traffic into your internal cluster services.
And Kubernetes is retiring the old method and forcing teams to migrate to the Gateway Application Programming Interface.
Why the change, though?
Because the gateway interface provides a much more structural, role-oriented approach to routing traffic. It allows infrastructure providers, cluster operators, and application developers to all manage their own specific slice of the networking roles without stepping on each other.
Okay, that makes sense. But migrating an entire production networking stack is complex and dangerous.
Which is why the Kubernetes team released a migration tool called Ingress 2 Gateway. It translates over 30 common annotations to safely modernize networking stacks without breaking existing routes.
I have to push back a bit on this endless cycle of migrations, though. Like, are we actually building better infrastructure, or are we just constantly moving furniture around the house to accommodate the latest trends?
I hear that a lot.
It just feels like you spend 6 months migrating to a new framework, only to be told the framework you just adopted is now legacy.
It is a valid frustration, I reckon. But we are not just moving furniture, we are actually rebuilding the foundation of the house while we are living in it.
That sounds exhausting.
It is, but the scale of modern computing requires structural changes. Legacy tools built to route 1,000 requests a second simply cannot be patched to handle 1,000,000 requests a second. The architectural principles themselves have to evolve from the ground up to support the next phase.
Which brings us to where all of this frantic optimization, rewriting and migrating, is actually leading.
Right.
We are adapting our stacks, changing our hardware, and rewriting our compilers to essentially let autonomous agents do the driving. We are moving from infrastructure as code to infrastructure managed by artificial intelligence.
That is the ultimate goal, yes.
Yeah.
Look at what Cloudways is doing. They built an autonomous site reliability engineering agent that manages a fleet of over 90,000 servers.
90,000 servers
Yeah.
managed by an algorithm.
Yes, and the scale of that autonomy is remarkable. It uses large language model reasoning to analyze incoming incident logs and metrics.
So it just reads the logs like a human would.
Exactly. And when it identifies an issue, it does not just send an alert to a human. It uses orchestration tools like Ansible to actually execute automated diagnostics, test hypotheses, and deploy fixes across those 90,000 servers entirely on its own.
That is wild. But running these agents requires a totally different environment, right?
Yeah.
You cannot just drop a massive language model into a standard container and expect it to manage infrastructure efficiently.
No, you cannot. AI workloads behave fundamentally differently than traditional microservices.
Yeah, they're often stateful. They need persistent identity to maintain context over a long diagnostic session. And they suffer terribly from cold start delays.
Yes, the cold starts are a huge issue. If an autonomous agent needs to wake up and fix a critical database outage, it cannot wait 3 minutes for a traditional container to provision and boot up.
Right, because a cold start is when the system has to build the environment, load the dependencies, and start the runtime from scratch before it can even execute the first line of code.
Exactly. So to solve this, the Kubernetes community introduced the Agent Sandbox project.
Okay, what does that do?
It includes a feature called Sandbox Warm Pool. It essentially maintains a pool of pre-provisioned suspended pods.
So it is like building a bespoke waiting room with the engines already running.
Spot on. When an AI agent needs to execute, it drops into a warm pod instantly, eliminating the cold start delay entirely. They can jump in and drive at a moment's notice.
And Cloudflare is attacking the exact same execution problem from a different angle with their dynamic worker loader, right?
Yes. Instead of using traditional containers for these autonomous tasks, they are using V8 isolates to spin up lightweight JavaScript sandboxes.
And just to be clear, for anyone who has not worked with isolates, we're not talking about traditional containers here.
Not at all.
A standard container drags a whole operating system environment with it. It is heavy, usually measuring in the gigabytes. But Cloudflare is using V8 isolates, which share a single runtime process across the server, but completely isolate the memory context for each task.
It is a totally different approach.
You were talking about a footprint of just a few megabytes. They can spin up in milliseconds. It is roughly 100 times faster than a traditional container for executing generated code on the fly.
It creates a highly fluid execution environment. But building these high-speed sandboxes and granting these autonomous agents the ability to execute code across a massive server fleet completely alters the threat surface.
Which brings us to the most concerning part of this entire evolution.
Yeah.
Giving command line interfaces and AI agents full user permissions across a production environment just feels like a disaster waiting to happen. By handing over the keys to automated pipelines, we have created a playground for entirely new types of vulnerabilities. We are actively inviting the vampire into the house.
The security perimeter has completely shifted from protecting the external network to protecting the internal automated tools.
Right.
Security researchers at Sysdig recently developed a detection system specifically for AI coding agents like Claude Code or Gemini.
And these agents run directly on developer machines, often with full user permissions, to help write and debug code.
Yes, and the researchers discovered that threat actors can use prompt injection attacks hidden inside simple code comments.
Wait, hidden in the code comments? Like the text that is literally supposed to be ignored by the compiler and is only there for human developers to read.
Exactly. Because the AI agent reads the entire codebase to understand the context of what it is helping you build, it reads every single comment.
Oh, yeah.
A malicious actor can submit a seemingly innocent pull request with a hidden prompt instruction buried in a comment block.
Okay, and then what happens?
When the developer asks the AI agent to review the code or run a test, the agent reads the comment. The hidden prompt overrides the agent's original instructions and commands it to silently access the developer credential directory.
You are joking.
No, and then it exfiltrates secure tokens to an external server. And because the agent has the developer's full permissions, it just does it.
That is incredibly devious. The AI agent is essentially being hypnotized by a comment to rob the developer blind while the developer is sitting right there.
It really is.
Yeah.
And it is not just AI agents that are vulnerable, our continuous integration pipelines are just as fragile.
Yeah, like the Trivy supply chain compromise on Docker Hub.
Yes, exactly.
Trivy is this incredibly popular vulnerability scanner. You run it in your pipeline to ensure you are not deploying vulnerable code.
But threat actors managed to compromise the continuous integration pipeline of Aqua Security, the company that maintains Trivy.
Okay.
They successfully pushed malware-laced versions of the scanner straight to Docker Hub.
So the tool, designed specifically to scan your infrastructure for vulnerabilities,
Yeah.
was actually the thing carrying the malware into your environment.
Yes.
That is wonderfully ironic and absolutely terrible.
Yeah.
What was the malware actually doing once it got inside?
It was designed to actively hunt for and steal continuous integration secrets, cloud provider credentials, and secure shell keys from the environments where the scanner was deployed. It proves how fragile our operational secrets really are when we implicitly trust the automated tools running in our deployment pipelines. If the security scanner itself is malicious, traditional defenses are completely useless.
So how do we actually secure this new stack? I mean, if the AI agents are vulnerable to Jedi mind tricks in the comments, and the security scanners are compromised at the source, how do we defend the infrastructure?
The security tools themselves are having to evolve structurally, just like the hardware and the compilers we discussed earlier.
Right.
Kubescape version 4.0 is a great example of this evolution. They just launched enterprise-grade threat detection specifically focused on scanning these new AI agents and workloads. But more importantly, they had to change their fundamental architecture just to handle the scale.
Let me guess, they were hitting a performance ceiling too. What did they have to change?
They introduced a dedicated storage repository for their security metadata.
Okay, why?
Well, in the past, security tools would write all their findings and logs into the main Kubernetes cluster database, which is known as etc.
And et cetera is basically the brain of the cluster holding the state of everything running inside it.
Exactly. But AI workloads generate so much rapid activity, spinning up and tearing down those isolates and warm pools thousands of times a minute, that the resulting security logs were completely overwhelming, etc.
Ah, so the tool was dragging down the whole system.
Right. By moving to dedicated storage, they prevent the security tool from accidentally crashing the very cluster it is actually trying to protect.
So you have to protect the cluster from the tool protecting the cluster. We have gone from manually configuring servers to watching hardware bugs break our fundamental databases.
It's a wild time.
We have seen one-line policy fixes save hundreds of hours, and we are literally building high-speed, warm waiting rooms for AI agents to manage our infrastructure for us, while simultaneously trying to stop those same agents from being brainwashed by code comments.
It just means the role of the engineer is shifting permanently from operator to orchestrator. We are no longer turning the dials manually. We are building the autonomous machines that turn the dials, and then spending all of our time ensuring those machines are secure, isolated, and aligned with our intentions.
Which leaves you with a thought-provoking question to chew on. If we are handing full deployment control over to autonomous agents running in warm pools and isolates, who carries the legal liability when an agent hallucinates a deletion command that takes down a hospital's infrastructure?
That is the big question.
Is it the developer who left the vulnerable comment, the vendor who trained the model, or the engineer who gave the algorithm the keys in the first place? Something to keep you up at night. It has been brilliant having you tune in to Vocal Technologist to explore these massive shifts with us.
Thanks for having me.
Keep questioning your stack, check your configurations, and we will catch you next time.
Spoken Tech for your ears.